Hi, and welcome to the Assembly Lines Podcast. I'm Chris Torrance. In this episode, we're going to take a look at fixing my Apple II emulator to better support graphics, sound, and hopefully, if there's time, also add support for Gamepads in the browser. So let's get started. In my last few episodes, I've been adding more and more features to my Apple II emulator in the browser. Last time I managed to get reading from disk images working, and at the end I showed a boot up of the game Snoggle. So let's take a look at that again. Alright, so you can see that the game works well and the sound actually is good, and we'll get to that in a minute. However, one of my viewers, Nelson Weissman, pointed out that the graphics looked a little wonky in the Snoggle game, and in particular, it looked like I wasn't quite handling the white pixels correctly. If you recall the way Apple II graphics work, if you have two adjacent colored pixels, those actually become white when they're displayed on a color monitor. And you can see that I'm handling that in some of the cases, but not all of them. Nelson thought maybe I was not handling it at the boundary between two bytes. So for example, bit 6 of one byte followed by bit 0 of the next byte, where bit 7 actually indicates which of the two different color sets you're going to be using for that byte. So I took a look at my code, and it actually turned out to be much worse than that. And we can actually run a simple basic program to see what was going on. Let me click on the disk drive to eject the floppy disk image, and then we'll just reset here, and we'll paste in an AppleSoft basic program that I've written. So let's go over here. Here's the program. Go back to my browser, and we'll paste it in. And this is just going to show all the different colors available on the Apple II screen. And so you can see it's running down the diagonals here. So what it's doing here is it's showing colors 1 and 2 next to each other. Here's colors 5 and 6 next to each other. And then these next two rows of colors are supposed to again be colors 1 and 2, but shifted by one column. So for example, here the purple color is in column 2 while the green is in column 1. And this should produce white, and it's not. And similarly for colors 5 and 6, this should also produce white. If we look at my code that actually converts the bytes in the Apple II's memory to colors on the JavaScript screen over in my Canvas file, we can see what's going on. If you remember from a couple episodes ago, I was actually doing two different passes. The first pass was to go through all 40 bytes in Apple II's memory and then break that up into the bits and assign each one to an individual color. And then I was doing a second pass down here where I would look at adjacent pixels. And I thought I was being really clever because I thought I only needed to look at every other pixel to see whether the two pixels were adjacent or not. However, you've probably already spotted the problem. If the first pixel of the pair starts on an odd number, so for example, pixels 1 and 2, then this loop here will never actually find those, and it'll never turn them to be white. So instead of doing I plus equal 2 here, this fix was really simple. I just needed to do I plus plus, so increment by 1 each time. The drawback of doing that is I then needed to add a third loop because I want to fill out the colored pixels so that they take up enough room on the screen. So you can see I'm doing that down here. Now for this loop, I actually can increment by 2 each time because I'm handling both the pixel as well as the pixel plus 1. So I'm actually handling both even and odd pixels at the same time. So let's go ahead and we'll save this, and we'll go back to my emulator now. And you can see that the code instantly updated, and all 4 lines at the top are now white. Let's go ahead now and boot up Snoggle and see what that looks like. I'm going to turn off the speed limiter here so we can boot up really quickly. And then we'll just fire up Snoggle. And then once it starts, I'll put the speed back down to 1 megahertz. All right, so you can see now that those weird color artifacts that we saw over in the T as well as in the numbers here on the right-hand side are all gone. The little Pac-Man guys also look correct, as well as all of the dots. So I think we've fixed all of the major graphics issues. Now, one thing I haven't tackled is actually the super high-res mode. Super high-res isn't the same as double high-res on, say, an enhanced Apple IIe or a 2C or 2GS. Instead, all that refers to is the fact that the colored pixels on an Apple II screen are actually a half pixel wide. And when you're looking at them on a color monitor, they get spread out, so it looks like it has the width of a full pixel. However, if you look at them on a green screen monitor, the pixels are actually half the width of what you would expect. And in fact, with some clever assembly language, you can actually plot 560 points across the screen. Now, this will look terrible if you then switch back to color mode, but it is possible to do. Now, my emulator only has an array of 280 bytes across, so right now it's just handling normal high-res graphics. But maybe in the future, I'll take a look at doubling the size of that array so I can properly handle that half pixel shift for colored values. One thing you may have noticed when I booted up Snoggle is that the sound actually sounds pretty good. If you'll recall from a few episodes ago, the only sound that I really had working was just a simple beep when the computer turned on. And this was sort of cheating. Anytime I saw that the assembly language program was hitting the C030 address, I would just play that normal beep tone for a tenth of a second. So you couldn't do any other sound effects on the Apple. However, I spent some time over the last few weeks working on the sound generation. I actually got a lot of hints and suggestions from subscribers to my YouTube channel as well as on Facebook. And in particular, I'd like to call out my fellow enthusiasts Nelson Weissman, Dionolium, Timmy TM Barrel, and Tomas Rudnai. All four of them gave me just enough clues that I was able to cobble together the correct code to do sound generation. The biggest problem that you run into when trying to emulate the sound on an Apple II or any computer with one of these 1-bit speakers is modern machines aren't really equipped to do that kind of sound generation. Instead, they're much better at playing actual MP3 tracks or creating beautiful sounding sine waves and things like that. But it's really hard to actually emulate a simple 1-bit speaker, which is a little ironic because that technology is so old, yet it's so hard to actually replicate. If we take a look at this diagram, it'll become a little bit more clear what's going on. Here we have a graph of the Apple II beep, which is at a frequency of approximately 934 hertz. I'm representing it as a perfect square wave, but if you actually look at an oscilloscope output from the speaker, it actually isn't really a square wave because of overshoot whenever it changes sign. So you can see that every time the address C030 is accessed on the Apple II, it actually turns the speaker on or off, or moves the diaphragm out or relaxes it. And so you can see that's represented as the waveform either going up or down. And this is how you actually produce sound on the Apple II, by just vibrating the speaker at a certain frequency. Now let's take a look at the code and see how I actually accomplish this using JavaScript. If we look at my motherboard.ts file, I have this memget function, and every time the Apple II accesses memory, it passes through this function to make sure that we aren't accessing one of the soft switches. So for example, here you can see we're handling the keyboard soft switch, and then down here, this is actually the speaker. So whenever someone does a load or a store or a compare or anything that's going to put the address C030 on the address bus, then we're actually going to click the speaker. And if we go over to my speaker file here, here's the click speaker routine right here. Now before, what I was doing is I was actually just trying to construct a square wave within here of a certain frequency and just play it. But this was incorrect, both because it always had the same frequency And because this was running in the same thread as JavaScript, you ended up with a lot of distortion as it would get interrupted all the time. I did a little bit of digging on this, and it turns out that there's a kind of lesser known feature of HTML5 audio support called the audio worklet. And to use this, you have to add what's known as a worklet module, which is a completely separate JavaScript file. And then you just wire up what's called an audio worklet node to your typical audio context, and then just start playing it. Now, what this does is this actually works in a separate thread. So it's independent of the main JavaScript thread. The way this audio worklet thread behaves is it operates at a frequency of 44,100 hertz. It divides that 44,100 cycles per second into cycles of 128 units long. And that works out to be about 2.9 milliseconds for each little unit. And it calls this audio worklet and passes it a buffer of 128 values, which you are responsible for filling in with the actual audio values. So let's take a look at my oscillator now and see what that looks like. And one thing is I wasn't able to actually write this in TypeScript because this add module just wasn't able to find the file anywhere other than in this worklet directory, which was in my public folder, which is part of my distribution. I don't know if there's a way to fool TypeScript into actually compiling the file and putting it into the correct location, but since this oscillator.js isn't that long, it really didn't make too much difference to me. If we go over to the audio worklet processor, this gets called every 2.9 milliseconds, and you can see this process method is what actually gets called. And it passes in three values: inputs, outputs, and audio parameters. So inputs would be, for example, if you had a microphone. Outputs is what we're interested in. And then you can also pass in optional parameters, which might be things like custom volumes or any other user-defined data. I'm not actually using that. What I do in here is I just pull out the appropriate output channel, and in my case, I just want the first output and the first channel. And then this is an array that's 128 values long, and you just fill it in with numbers. And whatever those numbers are, that's the waveform that's going to get played. If we go back to my diagram now and take a look, the bottom part of the diagram will now make a little bit more sense. So I have the 1 megahertz 6502 processor running, and for example, a sound of frequency 934 hertz, so this is the beep, that works out to a full period here of 2 times 546 cycles. So it's about 1100 processor cycles of the 6502 before it does a full oscillation of this square waveform from positive down to negative and then back up to positive. If we translate that to my audio signal from JavaScript, that's running at 44,100 hertz, so a lot slower than the 6502. And this works out to be approximately 23.6 cycles times 2 again. And then I'm given 128 samples at a time. And so all I need to do is just fill in these values and then translate from my 6502 time cycles, so the 2 times 546 cycles in this case. I switch that to the JavaScript cycles. So in my case, it would be about 47 cycles long. And I just fill this with, in this case, this run would be all ones, and then I would follow that with another run of negative ones, and then back up to positive ones. So let's look at the code and see how I accomplish that. Now, one thing I need to do is actually get that information over to the second thread, because the main thread is the one that's actually receiving the 6502 instructions, whereas the audio worklet thread is the one actually playing the audio. So if we look back at my speaker.ts file, whenever I get a click speaker, all I do is I just post a message to that secondary thread with the current 6502 cycle count. And this is what I'll need so I can do that translation from 6502 cycles into JavaScript cycles. And then over on my oscillator, I wire up the onMessage callback, and you can see here's the event. The event data is my 6502 cycle count that's coming in. I remember what the previous cycle count was, and then I just take the difference between those two, and I multiply by my sampling rate. And here you can see that's just 44/100 hertz divided by 1.02 megahertz. So this just scales from the 6502 to the JavaScript frequency. Now, this isn't always going to turn out to be a nice even number, especially with this kind of odd sampling ratio. At first I tried just rounding it off, but the problem is then you're going from something that's extremely high precision. So for example, the 546 clock cycles on the 6502 down to something that's only like 23 clock cycles on the JavaScript. And this was actually impacting the frequency of the outputted sound, and you could actually tell the difference between the beep of a real Apple II and the beep within my emulator. So instead, what I'm doing is I'm just rounding off to the nearest quarter. So I'm multiplying by 4, rounding, and then dividing by 4 again. This actually makes these samples sound a lot better. When I was writing this code, one of the things I struggled with was how to get from the message that gets called in to the actual process call. So you remember, this is happening on the time scale of the 6502. These messages could be coming in any random times, whereas this process function here is getting consistently called every 2.9 milliseconds with 128 samples. So I needed to have a way to translate from this message into something that the process could read at a consistent rate. I decided that the easiest way to do this is to just have a simple array of zeros or ones, and this is a circular array, so it'll just wrap around when you reach the end. So once I figured out the scaling between the 6502 and the JavaScript audio, I then just advance my index by that scaled delta amount, and then I just fill in a little value of 1, indicating that this is when the next transition should occur from positive to negative or negative to positive. And then down in my process method, I'm just looping through whenever I get called. Here's my 128 samples, and then I just index through this tick array 128 times. If I happen to come across the value 1, then I set it back to a 0, so I clear it out, and then I just flip the sign of the sample here. So my this.value is actually the volume of my signal, and you can see here I've just chosen it to be 0.1. So once I hit this little trigger, I set it back to 0, reset it, I flip the sign, and then I just keep going through the rest of the 128 samples. If I reach the end of the array, then I just go right back to the beginning. So this method seems to work well in principle. It's not perfect, and I'm still struggling with getting it to sound better for certain games or certain types of audio. One of the things I struggled with was the length of this little tick array here. If you make it too short, then what can happen is the 6502 will call this on message so frequently that it'll actually wrap around before my process has a chance to clear out the buffer. And so you'll actually end up garbling these signals because you'll end up with sounds overlapping one another. So there's kind of a sweet spot between using too much memory versus having garbled sound. Another thing that I'm not so happy with is that this is just a sharp transition between positive and negative. And I don't know whether that actually makes any differences for the Apple II sound or not. And then finally, I don't know if I'm really handling, say, store instructions correctly. So if we go back to my motherboard code here in the memget, you can see if you do like a load, say an LDA or a compare CMP, we're going to click the speaker. If I go down to my mem set, this would be like for a store instruction, so an STA, say store accumulator. If you do a store accumulator on C030, what the Apple II actually does in reality is it'll vibrate the speaker in and out really quickly. So on and then off, or off and then on. So it does a complete cycle. However, I'm not quite sure what that turns out to be in terms of actual sound. So all I'm doing is I'm just calling memget twice here when that happens. And so that will just call click speaker twice in a row. And if you look back in my oscillator code here, I have a hack where if I get the delta and it's actually the same as the previous delta, in other words, the delta is 0, then I just set it to some value here, say 3. So I just have some minimum kind of delay in the sound. And this doesn't seem to hurt anything, but it also doesn't actually fix any of the wonky sounds. So let's take a look now and see what sounds good and what doesn't sound good. Back in my emulator, you could see that when I did Snoggle, it actually sounded great. Okay, so you can kind of hear that little garbling, and that's kind of one indication that maybe it's not perfect. Let's boot up a sound generation program now and see what that sounds like. And these are just all programs from the Assembly Lines book that I've collected together into one disk image. And let's try and run the sound 4 file. And if we go into the monitor and then just go 300 go. So what this program does is it plays a continuous tone, and it's actually based on the ASCII character of the last key that was pressed. And so this will sound horrible, so I'm not going to keep it on for very long. But this is supposed to produce smooth, clear tones, and it does if you run it on a real Apple II or in, say, Virtual 2. But on mine, a lot of times it actually sounds kind of garbled. So let's take a look at what that sounds like. Okay, so you can see I just hit the letter A. Here's D, H. And you can see that I'm getting, we'll do, yeah. So you can see that every now and then it just sort of flips out and it does some sort of crazy sounds. And I don't know whether the buffer is wrapping around or whether my sampling is just not fast enough, or maybe my message passing can't keep up. So there's definitely some work to be done. Another place I noticed where the sound is a little wonky is in games that don't produce pure tones. So for example, let's look at Castle Wolfenstein. Okay, and we'll just hit K for keyboard here. And I've got it in sped up mode. And now let's just go back to regular mode. All right, so I'm just going to walk around. Let me turn up the sound a little bit. All right, so that doesn't sound quite right. And then if I bring my gun up, you can see when I fire, that is definitely not the Wolfenstein sound. Let's listen to it in Virtual 2 just to make sure that we know what it should sound like. Okay, we'll bring up our gun. So you can see that it has that kind of sharp guttural noise, which sounds fantastic. Clearly mine is struggling to do that. It's actually playing what sounds more like a pure tone. And I noticed that there actually are some store accumulator instructions that are being used. I don't know whether that's the problem or whether it's just the fact that maybe Wolfenstein is actually playing multiple frequencies at the same time, which was possible with the Apple II speaker with enough clever assembly language programming and nested loops. And maybe the way I'm doing that sound emulation just can't handle that. So there's still more work to be done. I'm happy with the way it is right now. For most tones, it sounds good, and I just need to make some more improvements. If you have any suggestions as to what might be going on, feel free to leave comments down below. I'd love to hear what you have to say. The last thing I want to talk about today is adding support for gamepads. Many Apple II games use the joystick, and it wouldn't be a really great emulator if I didn't try to support that. Now, it actually turns out that there's a really nice HTML Gamepad interface that you can use for just this purpose. I have a standard Bluetooth game controller. This is actually the GameSir T4 Pro, and this will actually work with pretty much any game controller that you can plug in to your Mac or PC. And the API that's provided by JavaScript lets you get access to all the buttons as well as the thumb controls. So I wanted to try to integrate this in with my emulator. And to do this, I just wired in support to my canvas. You can see that the standard browser navigator object has this get gamepads function, and this will just return an array of gamepads. I'm just pulling out the first one, and then I'm passing it to my handle gamepad function that I wrote, and I'm just pulling this every 100 milliseconds or a tenth of a second to see if a gamepad has been hooked up. And if it has, then I'm going to go ahead and loop through all the buttons. So let's take a look at that now and see what that looks like. Here's my handle gamepad function. This takes as input one of these HTML5 gamepads. And then the first thing I want to do is look at the joystick. So here's the X stick and the Y stick. And for example, on this particular gamepad, there's actually two of them. And so I take a look at either one. So it's either axis 0 or axis 2. And then same thing for axis 1, which would be up and down, or axis 3, which would be up and down on the other one. And I just look at whichever one. I think this one here has precedence. So as long as this is not equal to 0, then I'm going to read this one. Otherwise, I'll read this one. Now, what we need to do is actually convert the values that the gamepad returns, which are from the range -1 to +1, into the values from 0 to 255 that the Apple II expects. Now, you might think that you can just do a simple conversion, -1 to +1, into the range 0 to 255, and that would be great. However, that's not how the Apple II assembly code actually works. Instead, things are a little bit more brute force. The way the Apple II joystick works is it actually uses a simple resistor capacitor or RC circuit inside the computer itself. The joysticks have a potentiometer in them which has a range of 0 to 150,000 ohms or 150 kilo ohms. And the little RC circuit just measures how long does it take to time out. In other words, how long does it take for that capacitor to discharge? So we have to actually emulate the RC circuit with our emulator. If we scroll up to the top of my file here, I have a max timeout cycles. And this is the number of 6502 CPU cycles it would take if the joystick was all the way over to the right or to the bottom. In other words, returning a value of 255. And it turns out that the RC circuit has a timeout of 2.8 milliseconds. And that works out to be a little under 3,000 CPU cycles. So what I do then is I just scale this -1 to +1 of the joystick into the range 0 to about 2,800 CPU cycles. And then when my motherboard in the same memget function that we were just looking at, it's going to receive a couple different soft switches related to the joystick. The first is at address C070, and this is just the signal to the motherboard that it should charge the RC circuit and begin counting. So I have a reset joystick function when that occurs. And then when you actually try to read the joystick value, that's at locations C064 and C065. There's actually two other joysticks that you can read at 66 and 67, but we're going to ignore those for now. And then I call this check joystick values function. So let's take a look at these two functions right now. My reset joystick, I'm going to set the soft switch values here for the two joysticks. So the X is at 64 and the Y is at 65. I'm going to set those to have the high bit set. If the high bit is set, that means that the RC circuit has not timed out and it hasn't finished reading that joystick value. And then in my check joystick values, you can see that I've saved off the initial cycle count of the 6502 when you called reset, and I'm just taking the delta between that and the current 6502 cycle count. And if that difference is still less than, say, my paddle 0 timeout, which I calculated down below, then I return the high bit set. However, if the cycle count is now larger than this timeout, then I return 0. Now, what the 6502 assembly code is doing is it actually has a counter, and it's just calling this polling here for C064 over and over and over again and seeing what it gets. And it's just incrementing to, I think it's the Y register, 0, 1, 2, 3, 4, up to a maximum of 255. So as soon as this returns 0, then it stops that counter, and whatever that Y register value is the actual joystick value. So that's how the paddles work, or the joysticks. And then for the buttons, it's actually a little bit simpler. In this case, we just loop through all of the buttons and see, okay, if the button was pressed, then we're going to call a button press function. And I've actually pulled this out into an array here because there's so many different buttons. And then I'm just using, say, for example, the left joystick button would be the A, for example. The B would be the right joystick button. And I've programmed all the buttons to be either left or right, depending on which side of the controller they're on. And so the buttons are actually the simplest part of this. And if you want to figure out what the mapping is, there's actually a really good website here where it shows you the numbers for a typical gamepad. Let's just go ahead and we'll see this in action. I've got the game controller wired up. My code is running. Here is Choplifter, and I can actually go ahead and fly the chopper. And I'll hit the B button here to turn around, face different directions. And the sound actually is pretty good on Choplifters, so whatever I'm doing is actually not too bad for that. Let's take these people back here. One final thing, you might have noticed that I pulled that button code out into an array. And the reason I did that is I realized that these buttons don't all have to just be the left and right joystick button. You can actually have them do whatever you want. And in fact, what you can do is you can actually have them emulate Apple II key presses. So what I did here for this example, if we get rid of Choplifter and boot up Wolfenstein. Okay, so I can hit J for joystick, and we'll limit the speed now back to 1 megahertz. And now I can go ahead and I can use my joystick to move around. I can point my gun if I want to. Now, normally, if you were playing the game, you'd have to switch between using the joystick and the keyboard, because to look inside this chest, I actually have to hit the space bar. However, I've reprogrammed my gamepad now for Castle Wolfenstein. So I can actually hit this top left button here, and that's the same as the space bar. And now normally I would have to hit the U key to get the bullets, but instead I've programmed it so I can actually hit the X now on my controller and get the bullets. And then same thing, if I want to see my inventory, I can hit this right top button and it'll tell me that. So with this now, I can actually play the game without ever having to touch the keyboard. And you can imagine that there's a lot of other Apple II games which have a combo of keyboard and joystick, which could benefit from this kind of mapping of gamepad controls to keyboard characters. Okay, so that was a lot to cover in this episode. I hope you enjoyed it all, and we'll keep going next time. Well, I hope you enjoyed this week's episode. We took care of fixing some graphics issues. We also improved the sound generation. And finally, we added support for using gamepads in your browser. In the next episode, we'll either take a look at adding write support to floppy disks, or maybe look at binary coded decimal mode. If you haven't subscribed to my channel yet, please hit the subscribe button below. Also, I have a Patreon if you'd like to support me that way and get your name in the credits, and I'll have a link in the show notes for that. Once again, thanks for watching.